I welcome all of you to the class. As far as the today's class is concerned, in today's class we'll be talking about the inclined loads on the beams. Till now, as far as the loading condition on the beams was concerned, the load that was acting on the beam was in a direction perpendicular to the axis of the beam. Okay, so if we had a beam, if say for example this is a beam, and this beam is supported at the two ends. This is say for example support at end A, and this is say for example support at end B. Okay, then we were right now showing that the load is acting in this direction. So this is the beam axis, this is the axis of the beam, and this is the direction of, or the line of action of the load. So if you look, the line of action of the load is in the downward direction, and the axis of the beam is in this direction. So essentially the angle between them we are assuming is 90 degree. Okay, so the angle between the two was 90. But now this is not the only case. Sometimes the loads acting on the beam is what we call as the inclined loads. As you can see in figure 6.16, look, try to make a difference between the figure 615 and figure 616. The difference is, in figure 615, the load is acting in a direction perpendicular to the beam axis. Okay, while as in figure 616, you are having the load which is acting at some angle. Fine. So these types of beams we will be studying right now. Okay, number one. Number two is, when we say we have to study these beams, we mean to say we have to study the stress distribution in the beams and essentially the nature of the strain, the deformation in these beams. Before we go ahead, we are talking about the double symmetric beams or doubly symmetric beams. Though it's doubly symmetric beams, or we also call as the double symmetric beams. What do you mean by the double symmetric beams? Okay, if you look at the beam in figure 616, okay, so essentially you have a beam section like this. Okay, you have a beam section in the form of a trapezium. The cross section of the beam essentially happens to be a trapezium. Okay, now if you take this axis, say for example, if you take this axis is the axis which is dividing into your beam into two symmetrical portions, mirror images of one another. Okay, so this is the only axis of symmetry over here. Okay, I mean to say, though there is one more axis of symmetry, that is this. This is also the axis of symmetry of, is this also the axis of symmetry? No. So you have only one axis of symmetry of this beam, that is this axis. Okay, and this is dividing your beam into two equal parts, two symmetrical parts, I should say. So we say this beam is symmetric, but it's single symmetric. It has single axis of symmetry. This beam has single axis of symmetry. This beam is essentially symmetric. There is no doubt about its symmetry, but this is having single axis of symmetry. But if you look at this beam at the bottom, okay, now if you draw its cross-sectional area, the cross-sectional area is essentially in the form of the rectangle. Okay, so if you look now, this is one axis of symmetry, isn't it? This is one axis of symmetry. Okay, so this axis divides your beam cross section into two symmetrical portions. At the same time, this is also one more axis of symmetry. It also divides your beam into two symmetrical portions. The top portion is symmetrical, as well as the bottom portion is also symmetrical. Are you getting me on? So what is happening as far as this type of beam is concerned? We say this beam is doubly symmetric beams. These are doubly symmetric beams. They are having two axes of symmetry. Okay, so our entire analysis will be on these types of doubly symmetric beams. So what we have acting on these doubly symmetric beams is an inclined load. Inclined load can be any load. It can be a concentrated load acting at an angle. It can be a uniformly distributed load acting at an angle, or it can be a triangularly distributed load or a non-uniformly distributed load acting at an angle with respect to the axis of the beam. Now what we do, we all know that the external deforming force, the external force that acts on the beam, or the external load that acts on the beam, its tendency is to create stresses in the beam. Okay, and there are two types of stresses in the beam. You have normal stress, you have shear stress. When you talk about the normal stress in the beam, you use the flexural formula. Stress is equal to minus my divided by I. And when you have to calculate the shear stress, you use VQ divided by I into B, where Q is the first moment of area, V is the shear force, I is the moment of inertia about the neutral axis, B is the width of this beam. We all know these formulas. This formula is in fact known as the shear flow formula. We know these formula. We have already derived them in the previous lectures, in the previous class, Module 1. And this is our flexural formula. Okay. This is flexural formula. These two formulas are used for calculating the normal and the shear stresses. So if we talk about the normal stresses in the beam, the normal stress in the beam is essentially a function of the bending moment in the beam. Okay. So the formula that we have, the normal stress in the beam, sigma is equal to minus my divided by I. What is this M? This is the bending moment created in the beam. Are you getting me or not? So if we have to calculate how much is the normal stress created by this inclined load, we have to see the effect of this load, external load, in terms of the bending moment. Are you getting me or not? So first of all, we have to represent this load in terms of the bending moment. So what we do? So be careful and try to recognize what is this load trying to do. If you look at this load, you can resolve this load into two components. You can resolve this load into two components. This is the line of action of the load. This is the line of action of this load, isn't it? This is the line of action of this load. The load is acting along this axis. Okay. So essentially this can be resolved into two components. One component is in the downward direction and another component will be in this direction. So if you look at the bottom component, if you look at this component, this is component acting along negative y-axis, is parallel to y-axis, and this component is along the z-axis, isn't it? Are you getting me or not? So essentially, what is happening? So the load that is acting, let's suppose P, this load P is having two components. One component is along parallel to z-axis and its another component is parallel to y-axis. It's having two components. Okay. Now let's try to understand the effects of the two loads. If you see the component of load acting along y-axis, this is simply like a concentrated load acting along y-axis. Okay. So what will this component try to do? This component has the tendency of rotating this beam in this direction. Okay. Are you getting me or not? And if you curl your fingers, okay, if you curl your fingers in the direction of this arrow, then you will have the direction of the thumb will give you the direction of the moment. Okay. So if you curl your fingers, then your moment will essentially be in this direction. Okay. That will be the component of the moment M. Component of the moment along z-axis, we write that as M ZZ, and that is shown by two arrows. Now, if you look at the load along direction Z, okay, it's trying to rotate the beam. It's also trying to rotate the beam, and its tendency of rotation, what is it trying to do? It's trying to rotate the beam in this direction, like this. So if you curl your fingers, your thumb will be in the downward direction. So essentially your thumb will go in the downward direction because it will try to rotate the beam in this direction. Okay. So your thumb, the direction will be in the downward direction. We write that as MY or MYY, what we represented by double arrow. So important thing is the load that is acting at some angle, inclined load, it is creating the bending moment, isn't it? It is creating the moment. It has a tendency to rotate the beam, and one component is along z-axis, another component will be along y-axis. There will be no component along x-axis because for the rotation of the beam, for the moment along x-axis, then the rotation has to be in what direction? The rotation here has to be in this direction, which no component of the force here can do. Okay, so you have only the moment along y-axis, and we have the moment only acting along z-axis. There is no moment acting along x-axis. We write mx, moment along x-axis, is equal to 0. Fine. Now, if you look at the diagram, figure 517, figure 518, that is this diagram. This diagram is talking about the components of the moments along y-axis and moment along z-axis. It does talk about it. But if you look at the arrows, they are in a direction opposite to the arrows you have realized. Are you getting me or not? Your arrow for MZZ is in negative z-axis, but here MZZ is in positive z-axis. Your component for MY is along negative y-axis. Here component for MY is along is positive along y-axis. So what is it now? Why our arrows are in a direction opposite to the arrows in the book? The reason for that is the book is trying to give us the general expression. It's trying to give us the general expression. That's why it's assuming that the moments are along the positive y or the positive z direction, which by the equation of equilibrium will be rectified. Okay, that's not an issue for us. But what is very important for us is to realize the two important things, that we will be having the moment my and mz. Now, apart from these moments, now we know we can calculate the bending stresses. As far as the bending stress in the beam is concerned, that is very, very important for us. Okay, as far as the bending stresses in the beam is concerned, we'll return back. Now, the bending stress formula is, we can easily make an what's known as an analogy. Okay, we know the bending stresses in the beam has the formula stress, normal stress is equal minus m, this is the bending moment in the beam, y, the distance from the neutral axis, divided by I, where I is the second moment of inertia. Are you getting me? So now how many moments we are having? We are having two moments. We are having my and mz. So this bending stress will have the effect. We have to incorporate the effect of both the moment my and moment mz. Are you getting me or not? So how we do it? There are various ways of doing this, but we do the simplest of the methods. That is, the simplest of the methods is, let's suppose we are having a beam. Okay, let's suppose we have a beam cross section. Okay, and this n is our neutral axis. There is a reason for it. Now, initially in the previous cases, we were having neutral axis like this. We are assuming this axis to be the neutral axis. Sometimes this was matching with our z axis. Okay, so this used to be our neutral axis. But in case of the inclined beams, beams with inclined loads, the neutral axes are also inclined. We'll just prove it. Okay, so be careful about it. The neutral axes are also inclined. Number one is, we are assuming that the entire moments are concentrated at the centroid. Fine, that is a very important prerequisite for us, because this is an assumption. We're assuming the material to be uniform, not non-uniform. So we are having moment along y-axis, we are having moment along z-axis. Be careful about it. This is very much, it requires a lot of thinking. Let's assume that we are having a point A on the section of this beam, okay, such that the coordinates of this point are y comma z. That is, in order to reach to this point A, you have to move y along y-axis and you have to move z along z-axis to reach to this point A. Okay, now what will be the effect of my? What will be the effect of the moment y on point A? Is it trying to compress it, or it's trying to it's putting it in tension, or it's putting it in compression? It's putting it in my. So first of all, see, your my is in the upward direction. Okay, so put your thumb in what direction? In the upward direction. So what is the direction of your fingers? The fingers are circling your A. Are you getting me or not? Now see, what will happen to the A by the effect of this moment? It will try to put it in tension or compression. No, it will be in tension. Look again, just look into the diagram again. It's like this. Okay, it's like this. Now the moment is in which direction? Upward. So curl your fingers. Okay, but your point is where? It's on the it's mostly on the back side. And the point is somewhere here, isn't it? The point is somewhere over here. It's here. It's not here. It's not here. It's not here. It's somewhere here. Okay, so what is this moment now trying to do? Your moment is in the upward direction. So upward direction moment means this moment is trying to move like this or backwards, like this. Isn't it? So now we have a point here. What is this moment trying to do to that point? Tension or compression? Tension. And all the points that are ahead of the center line, they will be in compression. Okay. So this moment My is creating what? Tension on point A. Okay. So when you have My creating tension. Okay. So you have My creating tension, and this My at this point A is at a distance, is at some distance from y-axis as well as from z-axis. This is very important. So we will write My, moment My is creating tension. We'll write this as moment My is creating tension. Now tell me about Mz. What is this Mz trying to do? Yes. Mz is trying to do what? What is this Mz trying to do? What is Mz trying to do? Again, the same point A. Now, what is the direction of your moment? It's like this. Acting. So, moment will be acting in which direction? So, this is in this direction. Curl your fingers. So, what is happening? It's going like this. So, what will happen to the point A? जो point A आपका यहाँ पे था, ठीक है? ये curl हो रहा है, but it's now moving like this. So, what is happening to the point A? It is under compression. Just think about it. This is under point A is under compression. Point A आपका यहाँ पे. Point A is here. Okay, so your moment is in this direction. So it means it's being bent like this. So the top point, this point A is now under compression. Because of which moment? Because of which moment? Mz. So same point. Point A, because of Mz is under compression, and because of My is under tension. So we write Mz is creating compression at point A. Is this clear or not? You can think about it again. Just okay. So it's creating compression. Now get back. Now, when we had the previous cases, we had a beam section like this. Can you see this beam section? It had a beam section like this, and this used to be our neutral axis. This was our z-axis. This axis was our y-axis. This was our y-axis. Let's suppose we were taking a beam section here, which was at a distance y from the neutral axis. We were writing the normal stress there is equal minus My divided by I. Was this the formula? So this Y was the distance. But if you look at this moment M, this moment M was the moment along z-axis. This moment was the moment along z-axis. I will prove it. Why? Because your beam was essentially like this. This was the beam. We had this axis to be the x-axis. This axis was our y-axis. And this axis was the z-axis. Now, because of loading, there was bending moment. जैसे कि आपने यहाँ एक section लिया, you take a section over here, you are saying bending moment here is M. Curl your finger, tell me the direction of the bending moment. What is the direction of the bending moment? Along which direction is this moment acting? X or Y? Z. You take a section here. So you have a beam here. Now you say bending moment here is M. Curl your fingers in the direction of the arrow. What is the direction of the thumb? Outwards. That's along z-axis. Therefore, this moment is acting along what? This is along z-axis. So it means it was like this. If you have a beam and this beam is supported on two ends, end A and end B, if this is subjected to any load, let's suppose P. Okay, let's take moments about an axis passing through this point A. So the moment, if this distance is x, moment will be p into x. What will be the direction of the moment? Yeah, it will be along negative z axis. Are you getting me or not? It will be along this direction. So this is the direction of the moment. So the beam is, if this is your x-axis, if this is your y-axis, then essentially the moment, bending moment is in the beam is along which direction? Along z direction. Are you getting me or not? So look into this expression of the fluxural formula. We say stress is equal to minus my divided by I. Y is the distance from the neutral axis to the point where you have to find the bending moment, while the bending moment is along which axis? Z axis. Are you getting me or not? Now look into the expression. The total stress sigma x will be because of the two effects, will be because of two moments, moment mx and y and mz. Now let's talk about mz first, because this is quite easy. What is mz? Moment along z axis was trying to create compressive stress at point A. That's why this is minus. It will be mz, it is at a distance y, that is y divided by moment of inertia along z axis. No problem with this. Okay. Now what will be the moment? Because of the bending moment my, it is like your beam axis has now changed. The moment because of the stress because of my at point A will be positive because it's tensile. So we are writing this as positive. Bending moment is how much? My. Bending moment is along y-axis. Now you will take the coordinate z-axis. Okay, and moment of inertia about the same axis about which you are calculating the moment of inertia, that is y-axis. So this becomes the expression for your normal stress in a beam which is subjected to an inclined load. Okay, fine. That's why I am teaching this subject from the book, because if you don't have these diagrams, then it's very difficult. Are you getting me or not? Fine. Now, if this axis happens to be the neutral axis, if n axis happens to be the neutral axis, what's the condition of the neutral axis? Yes, on the neutral axis, the stresses are 0. So if this is the neutral axis, which is at an angle beta with respect to the z axis, then on this n axis, neutral axis, the value of myziy minus mzyiz should be equal 0. That is here. So we obtain, when you do the algebra, y by z is myiz divided by mziy. By the way, what is this y by z? In the right angle triangle, in this right angle triangle, this is y, this is z. Okay. In this right angle triangle, this is y, this is z. What is this y by z? Okay, this y by z is equal to tan of beta. Okay, that's why the angle that the neutral axis is subtending with respect to the z axis is given by this formula. That's why I said the neutral axis does not coincide with the z axis. Okay, fine. Any problem with this? Okay. Now, an important relationship is to be established between the neutral axis and the inclination of the load, angle of inclination of the load. That is something interesting for us. Why we are doing it? We are doing it because we need the results. Right now, we have established with the help of this tan beta formula that as far as our neutral axis is concerned, the neutral axis subtends an angle beta with respect to what? With respect to our, with respect to the z axis, undoubtedly. Fine. So we can at least say right now that our neutral axis does not happen to be the z axis. Okay, but our neutral axis is an axis which is as an angle beta with respect to our z axis. Fine. That's one important thing. Number two is Now let's see if now the load is being, because we know the load is acting at some angle. This is the load, and let's suppose this load is making an angle theta with respect to this z axis. Then what is the relationship between this beta and this theta? This is very important for us to establish the relationship between the angle of inclination of the load and this z axis. So what we do in order to establish the relationship, let's take, say for example, at this picture that is 6.19, the figure 619 of the textbook into consideration. It says what we are doing, we are right now assuming that the load is acting at an angle theta with respect to the y-axis. Okay, this is quite genuine reason for it. We can make an angle with respect to x-axis, with z-axis. That's not an issue for us. Okay, we need to start the analysis somewhere. Okay, then, and this load is being assumed to be acting in this direction, while as essentially the load should have been in this direction. There is a reason for it. The reason for it is, can you tell me what could be the reason for applying the load P in this direction? See, this is what the academic diagrams and academical assumptions are all about. Okay, I mean to say is, for example, if you have to analyze the car, the shaft of a car, you assume that the shaft is made of a material having constant properties in all the directions, but that's not the case. Okay, so these are our academical diagrams because we want to reach to the results, okay, by which we can start designing process, by which we can start the analyzing process. Okay, so this is again an academical diagram because by applying the load P in this direction at point A, because of load P, moments My and Mz will be created. Okay, moments My and Mz will be created. But I think the influence of My and Mz at this point, at any point A here, will be creating the positive stresses only, no compressive stresses. You try to see it. It creates only the positive stresses, no compressive stress. Okay, anyways, let's at least assume that the load P is acting at an angle theta with respect to the y-axis. So load P is acting at an angle theta with respect to the y-axis. Let's suppose we are having moment My along y-axis, moment Mz along z-axis, and let's suppose the neutral axis is subtending an angle beta with respect to the neutral z-axis. Okay, and theta is the angle between the load and the yes z-axis. Fine. Yeah, y-axis. Okay, now let's take the components of P. P is having two components. Let's take the components of P. P will be having two components. One component of the P will be in this direction. That will be, sorry, it will be in this direction. Yeah, that will be, sorry, in this direction. That will be P cos theta. Another component will be in this direction. That will be P sine. Let's take a section out here, just as it is drawn. Okay, such that this section is at a distance. This section is at a distance x from the fixed end. Okay, therefore, how much will be its distance from the free end? L minus x. How much will be the moment at this end? How much will be the moment here? Because of P cos theta, moment will be P cos theta into L minus x. And what will be the direction of this moment? Yes, it will be along z axis. Okay, and what will be the moment because of P sine theta? It will be P sine theta into force arm is how much? Again, L minus x. Okay, so if you look here, the moments at the free end will be, as is given here, is correctly saying that the moment is along z axis is P cos theta L minus x, and this is the moment along y-axis. Okay, because your p sine theta is along this direction. It's trying to rotate the beam in this direction. Curl your fingers, the thumb is along y-axis. Okay, then divide my by mz. What is my by mz then? Divide these two formulas. My by mz will be equal to how much? Yes, L minus X will cancel, P and P will cancel, sine theta by cos theta will be tan theta. But we know, we have just derived tan beta is equal to my by mz iz by iy. Therefore, that was equal to my by mz is equal to tan theta. So we'll write this as iz by iy into tan of theta. Okay, therefore we obtain tan beta is equal to iz by iy into tan of theta. This is the relationship between beta and theta. What is beta? The angle which the neutral axis have moves. That's all for today. And tomorrow we'll be talking about the unsymmetrical beams, and tomorrow we'll be talking more about the shear flow formulas. Thank you.